All right, guys, welcome back. So today we're going to use Colab and play with that abalone data set that we discussed last time to kind of go deeper into Nystrom Approximation, which is the topic that we discussed last week. And then we're going to see the actual implementation and get a feel of how it works and things like that. So I'm going to drop the source code in the chat so that you can just copy and paste the source code for initializing Spark. Okay. And then also there's another code cell to download the data set. So it's from the UC Irvine machine learning repository. And there's this abalone data set, which is really, really popular data set. So I'm going to give you a couple minutes for you to open up Colab and initialize your environment with Spark. And while you guys are doing that, let me actually try to pull up the lecture notes. I believe Nystrom approximation is something that a lot of people kind of struggle to understand. So maybe it might be good to, for today's class, sort of go over the lecture slide and then see how things are implemented side by side. Okay, so just as a recap, this was the idea. So in the data set, obviously computing distance matrix is kind of really expensive, and what you would like to do is basically to approximate a distance matrix using only a partial information. So now let's say you have some points, which are called the pivot points. And then for the pivot points, you basically know the distance among each other. So that's the block matrix A over here. And the block matrix A is essentially, a distance matrix among this pivots. Now, after that, for a given reference points, so the reference points are the ones that are in the training data set. And for the reference point, we basically compute the distance from each of the reference points to all the other pivots. Okay, so distance from 1 to 6, 3 to 6, 2 to 6, 4 to 6, those are computed, and that's the block matrix corresponding to this block matrix S, right? And then for a given query, what you do is then instead of searching exhaustively across all the data points, you simply just calculate the distance from the query point to, those pivot points. And then using that, the conclusion was we could compute the distance from the query to all the other points in the training data set. So all the other reference point in the training data set by conducting this simple matrix operation where BA, so A is the distance matrix among the pivots, and then B is a distance matrix showing the distance from the reference points to the pivot points. And then, so B transpose A inverse was basically something that you could calculate agnostic to the query points. And then C was basically the matrix showing, the distance from the query point to the pivot points, right? Which is, something that you can fairly quickly estimate. And then, the distance matrix from the query point to all the other reference points, which is going to, we're going to call D, is something that can be algebraically estimated by multiplying B transpose A with A inverse with C, okay? So that was kind of a recap of the Nystrom approximation. If things are not super clear, don't worry. The whole point of today's lab section is to give you a more solid understanding of what's really happening. So as we write code, I think things will become much clearer. So that's kind of the objective for today's class. Okay. So with that being said, I hope that everyone had a chance to run this code to initialize the Spark environment and download the data from the UCI machine learning repository. Okay. In fact, for today, we're not going to use Spark too much. We're mostly going to use this for reading the data set and then creating a data frame, and then the rest is going to be numpy. But I think it's a good kind of chance to kind of brush up what you've learned so far. So hopefully by this time, after finishing, a couple of projects, I think you became a sort of an expert in Spark. So as usual, what I'm doing now is I'm creating an app. I'm going to create an abalone app, and get or create is what I'm doing over here. And that's my new Spark session that I just created for this problem. Now, using that, the next thing I'm going to do is to, read the data file and, parse the information. So here, I'm going to just copy this URL in my web browser so that you guys can see the contents of this data file. There. So here is that abalone.data file, which is comprised of a bunch of numbers like this. So each row, again, is a row representing a data point, an observation. So that's one abalone. And then we have a bunch of numbers. And then they're all comma separated. So again, spark.read.csv is the function that we'll be using. Okay. So what happened to my cursor? Spark.read.csv, and then abalone.data is the file name that we've just downloaded. And then I don't know if you noticed, but this is a CSV file that just start with the data entry right away without any header. So there's no header. So we're going to specify that there's no header to read. And then to make things easier, we're going to just infer schema. So nothing really new. And let's see if the data frame has been loaded properly. So after a while, you'll see the data frame displayed on the screen. And as you can see, it looks all right? So the first row was M 0.455, 0.365, 0.095, and so on and so forth. It seems like they're all kind of correctly loaded. One thing I don't like, though, is the fact that the column names are not specified. So this is some, we saw this trick last week, right? In terms of how you could specify column name, which is the function called the with column renamed. So with column was basically a function to create a new column based off of some formula. With column renamed is basically creating a new column with a new name. So for example, I'm going to change the column C0 into a column named sex. And by the way, that detail is defined in the dataset website. So if you actually go to this URL and take a look at the data description, you'll actually see this thing called an abalone.names, where it specifies all the details in terms of what each of the columns indicate. Okay, so I'm basically just using that to, oops, where's my cursor? I'm basically using that to rename all the columns. So the second column is C1. By the way, if you don't want to type this, you can just leave the column names to be C0 to C8. It doesn't really matter because at the end, we're not even going to use the column name. So I'm just showing you some useful practical tricks that you can use. So in fact, I think, yeah, let's not waste our time renaming all the columns. Maybe you guys want to rename the first column, because first column is something that we're going to kind of transform. Right now, it's a categorical variable. So for sex of abalone, we have 3 different categories. One is male, the other is female, and then the last thing is infant. So we have either M, F, or I. And then we're going to convert that into a new column. Okay. So let's actually not bother to rename the columns. And I'm just going to keep this like this. And then that's basically what we'll be doing. Now, if you were successful in reading the data frame, here's the new cell that I'm creating. So like I just said, this column over here is comprised of the string variable. So what I want to do is actually to create new columns, okay? And then we're basically going to add a dummy variable indicating the sex of abalone. So here's a trick. So last time we saw this example of using this thing called a string indexer. And then string indexer was one of the estimators, which you could use to generate a transformer that transforms a table, right, into a new table that is with this column, mapping the categorical variables into numerical indices, right? So we saw this example of using string indexer from our previous lab sections. Now, I'm going to teach you a slightly different trick, just for the sake of giving you much richer kind of, set of skills to do the similar kind of things, which is a trick of using df.width column. So what I'm going to do is to create a new column called M. And basically this new column is going to be set to 1 when the sex of abalone is male. And then I'm going to set it as 0 otherwise. So for infants and female, we're going to set it 0. And for that, I actually need a helper function, which can be imported from pyspark.sql.functions. So I think you saw this already multiple times, right? So the functions module is a collection of helper functions, which can be useful for this kind of scenario. So when, okay, f.when, df sex equals to m, okay? So when the contents of the first column equals to the string m, then I'm going to set the value to be 1, dot otherwise, I'm going to set the value to be 0. Okay. So it's actually pretty simple syntax, right? F is alias for this module, pyspark.sql.functions module. And then f.when, oops. And when the condition is satisfied, this is the value that you're going to have. Otherwise, this is the value that you're going to have. Okay, so it's actually fairly simple syntax. So I hope you guys, can make sense out of it. Similarly, I'm going to create a new column called F, standing for female. So for female abalones, we're going to do the same thing. So when df sex equals to F, indicating female, we're going to set this column to be 1. Otherwise, aka males and infants, we're going to set it to be 0. Okay. And then after doing that, I don't actually need the column for that categorical variable. So I'm going to just drop the column name sex. And here's what I get after doing all this. So now you notice that, previously in the original data set, we had a column named sex, but then now it's gone because we dropped that column. Instead, we created a new column called male and female. In case of male, the first 2 rows, in fact, are males. And then in case of male, we have 1s for this M column. And in case of female, we have 1s for this F column. And then in case of infant, which is a 3rd category, then both of the columns are going to be set to 0. So that's the representation that we're using for this particular example. So you already know, multiple different ways in terms of converting a categorical variable into, a numerical index or a dummy variable. So whichever way you prefer, you can go for it. So string indexer was one excellent way of, converting a categorical variable. And then, this one over here is another, excellent way of converting, a categorical variable into a numerical indices. Of course, you don't want to do this when you have many, many, many classes. In our case, we have only 3 different classes, male, female, infant. So it doesn't really matter. It doesn't bother you too much to write all this. But in case you have 1,000 different categories, obviously this is not the way to go. Now that we have processed the table, okay, this is the data table that we'll be working on. Now, one thing I forgot to mention is that the C8 column is the one that represents the age of abalone. So if you actually go to the data description, the C8 column is the number of rings in abalone. And the number of rings plus 1.5 gives the age of abalone in years, okay? So according to that, what we're gonna do is to create a feature vector using all columns except C8, okay? Which is gonna be our data matrix X. And then we're gonna extract the C8 column, and that's gonna be the response variable, Y, in our formulation. So this is the part that, where we start to, we stop to use Spark, and then we're gonna convert everything to numpy. I'm gonna explain why we're doing that very soon. But for now, let's just, create a new data frame by dropping C8. And that's gonna be converted to numpy array by calling this. Okay, let me explain what this code means later. And that's gonna be our variable X, which is the data matrix. And then our matrix Y is a set of response variables, which is basically, instead of dropping, we're gonna select C8. And then we'll convert this into numpy array. And just to show you what happens, here's the result printed out. So as you can see, X is an array which is comprised of all the values here, including 0.455, 0.365, 0.095, 0.514, 0.2245, 0.101, 0.15, and we skip C8. After 0.15, we skip C8 column, and then the male column and the female column. So male column and the female column. The second row, same thing, right? So that's the variable X. And then the variable Y is basically just this column C8 extracted out of Spark. Okay. So this is, again, this is something.
Can you explain that once again?
Sure, yeah. So C8 is the age that we're going to predict. And then all the other columns are the features that we're going to be using to predict the age, right? So basically what's happening over here is we're splitting, the features with the response variables. So df.drop is going to create a new data frame without C8 column. That's what basically drop means. We're dropping that column. So all the other columns except C8 is going to be used to create this variable X. So as you can see, you can match the numbers, 0.455, 0.365, 0.095, and yada, 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 all the way up to 0.15. But then we skip C8 column, which is 15, right? And you don't see anything over here. And then the male column 1, female column 0. And then if you go to the second line, second row, it's more or less the same thing. So 0.35, 0.35, 0.265, 0.265, and so on and so on, so forth, all the way up to 0.07, which is the C7 column. And then we skip the C8 column and then go to the male column and the female column, male column and the female column. So that's what's happening. Versus Y, the variable Y here is df.select. So we're extracting only this column. So as you can see, the C8 column start with 15 for the first row, 7 for the second row, 9 for the third row, and so on and so forth. Now here, .to pandas, for those of you who are, not familiar with Python that much, pandas is a Python library for data analysis. So Apache Spark, PySpark, has a functionality where you can interface with pandas library. Pandas library is like the most popular library among data scientists in Python environment. So a lot of people are already familiar with pandas, and the decision of the developers of Apache Spark was that since so many people are already familiar with pandas, let's make Apache Spark compatible with pandas. So from a data frame, you can actually export your data table, your data frame into pandas data table. Unfortunately, Apache Spark has not provided any functionality to convert a data frame into a numpy array. So that's why we're converting Spark data frame into a pandas data frame, and then to convert pandas data frame into a numpy array. So that's basically what's happening over here. Okay. So this is kind of a small little trick which you can use to convert a Spark data frame into a numpy array. Obviously, if you have a big data, this is not a good idea. Okay, I'm doing this only because, first of all, the abalone data set is not that big. We have about 2,400 data rows, which is not a lot. So converting from a Spark data frame to pandas data frame and then to numpy array, there's not a computational load too much, right, for that conversion. Obviously, if you have millions of rows, doing this is a crazy idea. Okay, but I'm doing this just for the sake of making this tutorial much easier to understand. Again, Apache Spark has linear algebra library, which you can use to conduct, numerical operations, such as, computing the matrix multiplications or, computing inverse of a matrix and so on and so forth. So we can do that actually without having to convert into NumPy. But then, Nystrom approximation is already quite difficult to understand mathematically. And if I, on top of that, if I throw at you, some like Spark syntax, then it's going to make this tutorial really difficult. So that's basically why I'm converting everything into NumPy array. Okay, so I hope that makes sense. Now, the next thing we're going to do is then, the actual Nystrom approximation part. So this is the main deal, in fact. So we're going to define, for convenience, two variables. One is the variable named n, and then the other is a variable named d. So we're going to basically use the same notational convention. So n is for number of rows, number of objects in our data set, and then d is the dimension of the feature. So that means the first dimension of the data matrix X is going to be our variable n, and then the second dimension of our data matrix is going to be our feature dimension d. So just in case you're curious, we have total of 4,177 rows. Maybe I was wrong about the total number of data rows. It's 4,100 as opposed to 2,500 that I said earlier. And then the dimensionality D is 9 over here. So we have 9 columns, basically, length, C2, C3, C4, C5, C6, C7, M, and F. Those are 9 columns that defines the features, okay? So we have that over here. Now, using that as a warm-up, we're gonna implement here naive version of distance calculation. Distance matrix calculation, to be more precise, where I'm going to use some really brute force approach to compute a distance matrix M, which is defined to be n by n matrix. So I'm going to initialize the matrix M to be 0, filled with 0. And here is where we're going to implement a naive brute force calculation of the distance matrix. So for this, actually, I'm going to actually ask you guys to try to do it by yourself, okay? I'm going to give you about 5 minutes. What you're going to do is to work as a group to figure out how to implement naive version of distance matrix calculation. So basically, you're going to visit like all possible pairs in the data set, and then you're going to compute the distance between all those possible pairs, and then you're going to construct this distance matrix M. Okay, that's going to be your mission in the breakout session. Now I'm preparing to put you guys out to the breakout rooms, and and then the breakout room is going to be 5 minutes, and after 5 minutes, there's going to be a countdown. So, all right, guys, have fun. All right, so I guess everyone is back to the main room. So I don't know what kind of ideas have you guys come up with, but you know, in case you want to share the way that you implemented the code, feel free to just drop that in the chat. In the meantime, here's kind of a really simple version that everyone can understand. So basically what I'm going to do is to visit, you know, all elements, okay, in the matrix M, and then I'm going to just stick with the definition of the distance matrix. So I is an index indicating the row of the matrix M, and then J is the index indicating the column of matrix M. So basically, Mij is going to be the way that we'll visit, you know, each element in the matrix M. Okay, and then the definition of the distance matrix is that, you know, the Mij is basically the distance from the ith element in our data set, and then the jth element in our data set. So the let's say we have some distance function, right? And then we basically want to compute the distance between the ith row, right? And then the distance from ith row to the jth row, right? So that's basically what we would like to do. And here for distance matrix, let's say we want to use a Euclidean distance, simply because that's the easiest to implement, right? So then, you know, what I'm going to do is basically to compute the difference between the ith row and the jth row. And then what? I'm going to take the square of that difference. And in Python, it's double star. And the square of that is going to be summed up. And that's numpy.sum. And I guess we need to import numpy as np. And then finally, we need to take the square of that summation. That's the definition of the Euclidean distance. So this is essentially the simplest version of distance matrix calculation, right? So again, we're basically just traversing all the elements in the matrix M. So we visit the ith element and the jth element, sorry, the ith row and the jth column. And then for that ith, you know, column and the jth, sorry, ith row and jth column, we basically compute the Euclidean distance between the ith row in X and the jth row in X, okay? Now, if you try to be a little smarter than this, obviously you'll realize this is kind of an abundant, I mean, unnecessarily repetitive, because one property that we know is that the distance matrix is symmetric. So the distance from the ith row to the jth row and the distance from the jth row to the ith row is the same. So you don't actually need to do this twice, right? So then if you decide to be smarter, then, you know, this is probably what you're going to do. So instead of visiting all j, we're going to visit only j that is bigger than I, which means the upper triangle, right? And then, you know, simply just, you know, repeat the same value. And that's one of the ways that you could, you know, compute the distance matrix in a little bit faster fashion. Of course, there can be many different ways of implementing, you know, a code for computing the distance matrix, but this is probably the easiest to understand. So that's why I'm showing you this. So that's the way that we're calculating the distance matrix in a naive way. Now, let's try to measure how long it takes to compute this, because it's kind of nice to, you know, see with your eyes how long it takes to do this kind of computation. So remember, the matrix X has only 4,000 rows, which is not a lot, right? It's a small data. Now, what I'm going to do is to measure time, and I think I introduced this a couple lab sections ago. Basically, time.time is a function that returns the current time. And what I'm going to do is to define a variable called begin, which is the time right before computing the distance matrix. And then, you know, we're going to call time.time again right after all this for loop is done. And then we're basically taking the difference between, you know, the time when we started and then the current time after finishing the for loop, and excuse me, basically I'm just going to print out the elapsed time in seconds. Okay. Now I'm running the code, and I'm waiting. Still waiting. Nothing happens. Still nothing. So in my experience, this takes about 1.5 minutes, roughly. Despite the fact that we're somehow, making the computation more efficient by doing this trick, right? So we're only computing the upper triangle, but still takes quite a bit of time. Now, while we're waiting, let's make some progress. In order to talk about the Nystrom approximation, what I'm going to do is to split the data set into pivot points, reference points, and query points. Excuse me. And in order to do that, we're going to use a helper function. I mean, no, well, let's not worry about the helper function. So I'm going to just use this, the most straightforward way. So n in total was 4,177, right? So that's the total number of data points. There you go. The results finally came out. It took 110 seconds, which is almost like 2 minutes. So it's only like 4,000 by 4,000 matrix, and then computing that actually takes quite a bit of time. Okay. Later on, we're going to compare this with Nystrom approximation, and then you'll realize the computation is much simpler. So, anyways, so the total number of data is about 4,000, and what I'm going to do is to define to split this into some number of pivots. So NP is my variable defining the number of pivots, and what would you like to do? Maybe 20 pivot points. Okay. Let's do 27 so that, the numbers get less dirty. And then let's say for number of queries, so just to make sure, number of pivots, that's what NP is about. And then let's say we have 150 queries. Why do we have so many queries? Well, it can happen, right? If you have a large server, then you can have multiple queries at the same time, simultaneously coming in. So let's just simulate a scenario where you have 150 queries coming in, all together. So that means if you do the math, for the reference, we have 4,000, right? Which is basically n minus np minus nq, right? So that's So that's basically how we're going to split up the data set. So again, we have 27 pivots. We have 4,000 references, and these two comprises the whole training data set. And then 150 is basically the query data set. Okay. Now, using this, what we're going to do is then to split up the data set. So let's create, for example, pivot X. Well, X pivot might be a better naming. So X pivot is going to be the first 27 data points. So that's going to be, from the beginning to NP, which is 27. And then we need the reference points. And let's call it just ref, make it simple. And that's going to be from the next 4,000 points. So that's going to be then, NP plus NR, I guess, right? And then this. And finally, X query. And that's going to be from NP plus NR all the way through the end. I hope that's right. We can always check. So there we go. So we have first 27 rows, which we're going to use as a pivot data set. And then the next 4,000 rows, we're going to use as the reference data set. And then the last 150 rows is basically our, query data points. Now, I don't actually need it to print this out. With the same logic, we're going to do the same thing with Y. So we're going to need the Y pivot, which is, same set of index. Y ref, the same thing, NP through NP plus NR, and then Y query is Y NP plus NR through the end. Okay. So that's a basic split of the query and pivot and reference. Now, what we're going to do is to, first of all, implement the distance matrix among pivots. Okay, so let me go back to this lecture slide. The very first step for Nystrom approximation was to compute a distance matrix among the pivots. Okay, so basically we need to construct a full distance matrix among pivots. And for that, what we have done earlier is going to be extremely useful. So I'm going to just copy and paste. And instead of M, I'm going to call it A. Okay, following the notation in the lecture slide. So we have matrix A, which in our case is a 27 by 27 matrix. So 27 number of pivots, NP by NP. So instead of N, I'm going to change it to NP. And then instead of M, I'm going to use a new symbol A. And that's basically, and then, instead of the whole data set, I'm going to need only the pivot points, right? So again, because of my laziness, I just copy and pasted the same code from the above, but it's actually a good exercise for you to kind of, type it in from the scratch, because the more, you become familiar with this kind of implementation, the quicker you can grasp the mathematical concept. So, but for the sake of, finishing everything on time, here it is. Now, just out of curiosity, let's measure how much of time is required to compute this pivot distance matrix A. And surprisingly, excuse me, it takes only 4.6 milliseconds. So obviously, for the full dense distance matrix, it took about 2 minutes. This one, since we have only 27 by 27, so that's the size of NP, right? So since we have 27 by 27, the computation of this is actually pretty simple. Now, what's next? Now we have this matrix A over here completed. The next thing to do is to compute the matrix B, right? Which is the matrix indicating the distance from the reference points to the pivot points. So this one is a little trickier, which is why I suggested you guys to, practice implementing this, so that when there's a variation, this is kind of a variant of the distance matrix, right? You have an ability to implement them correctly. So basically, if you look at the anatomy of the matrix B, we have the number of rows that correspond to the number of pivots, right? We have 1, 2, 3, 4 pivots, and we have 1, 2, 3, 4 rows. And then, the number of columns of the matrix B correspond to the number of number of references. So in our case, instead of 4 by 2, it's going to be 27 by 4,000, right? So that's the matrix that we're talking about. And what I'm going to do is, basically mimic this routine, but I'll make a slight variation. So first of all, I need number of pivots by number of references matrix, right? That's the anatomy of, that's the dimension of the matrix B. Now, since the rows correspond to pivot, the row index I is going to range in NP. But then the column index J is going to follow the number of references. And in this case, we're not going to apply this trick, okay? Because this is not a symmetric matrix. This is not even a square matrix, as you can see, okay? So we have to compute everything in an exhaustive fashion. But anyways, the element ij of the matrix B is defined as what? is defined as the distance from a pivot point to a reference point. So a pivot point indexed by the row index I to a reference point indexed by the index j, right? And that's the distance that we're looking for. And then the rest is, pretty much the same. Take the square of the difference, and then the difference squared is summed like this. And then the summation of the square difference is square rooted. And that's basically the definition of the Euclidean distance. Agree? Now, that's done. That's it. And, out of curiosity, let's measure the time requirement. So begin equals to time, and then here I'm going to just directly print out time minus begin. And this one takes a little bit more time than matrix A because this is a lot bigger than matrix A. So, obviously it's going to take more time, but still not horrible. It's only, 1.4 seconds. Now, what's next? After matrix A and B is computed, remember, matrix A and B are the ones that could be computed offline. So we could compute this in advance before even to see a query, right? So here is my next step where I'm going to be computing B transpose times A inverse. Okay, that is something that I needed to do. And where's my cursor? Oh, here. So for that, I'm going to use np dot matrix multiplication. And then I'm going to multiply B transpose with the inverse of A. And the inverse of A could be computed using numpy linear algebra library dot inverse. Right? So this is basically for computing B transpose times A, inverse. Okay? Which is what's in the lecture slide, right? Now, that was a third step, which, well, I should have shown you the time. So again, this is an offline computation, but the total amount of time required to compute this is still 1.5 milliseconds. So it's negligible. So as you can see, in offline, the majority of computation happened, for the computation of B, which is the distance matrix from the pivots to the references. So, if you can afford computing this, in offline before receiving queries, you're all set to go. Now that we have this B transpose times A inverse, the next thing we're going to do is, this is where we are now ready to go online. And, users are sending in queries. Okay, so from this cell over here, this is what's happening online. Everything could happen, before this could happen in offline. And now this is where the users sending in queries. Okay. Now, for that, what we need to do, let me, try to show you the lecture slide. Now, what you need to do is for a given query, you need to compute the distance from the query to all the other pivots. Okay, so that is something that you're going to run immediately after you receive queries. So here, the matrix C is defined to be np.zeros. And if you think about it, we have the total number of rows corresponding to the number of pivots, and then columns representing to the number of queries that you received. So it's going to be basically NP by NQ matrix. And we're basically going to repeat the same thing as we did in matrix B. So again, for the I index from 0 to NP, because I index is for the row index, and then J is for the column index, and we're going to range it from 0 to NQ. And then Cij is basically an element indicating the distance from what? Distance from pivot, the ith pivot, to the jth query. You see? So again, we're computing the distance from the pivot to the query, each of which indexed by the row index I and the column index J, respectively. And we need to make it a Euclidean distance. So np dot square root np dot sum. I'm just going to do everything once like this. And that's our matrix C. And this is runtime. So it is important that this happens in real time. So let's see if that's indeed the case. So there we go. For processing 150 queries, it took only 59 milliseconds, which is quite nice, right? So to process all 150 queries, it took only 59 milliseconds. Now, using this, okay, this is the final step. Remember the formula? Using this, you can compute the matrix D by multiplying B transpose A inverse to the matrix C that we just computed. And then what this D represents is the distance from the query to the rest of 4,000 reference points that we don't know the distance. So for that, here's one final step. The approximated, okay, is what? Is NP dot matrix multiplication. We already computed B transpose A inverse in advance. So we're going to just recycle that. And then C is something that we just computed in response to the user specified queries. And this is basically the computation that we need to do to approximate the distance from the query to all the rest 4,000 reference points. And again, let's measure time. And for that, it took only 3 milliseconds. So again, we have 150 query points, and then to process all of them, it took 0.03 seconds for B transpose A inverse times C, and then it took 0.59, so 59 milliseconds for constructing this matrix C. So in total, it took roughly 60 milliseconds to respond to 150 query data points, right? Which is quite phenomenal, right? Now, so this is kind of a real-time response. Now, one thing that we don't know yet is if this approximated values are good enough, okay? So to validate if this approximated value, we're gonna do, a computation over here. So this is kind of just for validation. So we don't actually need to run this in real time. In real time, these two cells are basically the ones that you need to perform each time you're receiving query. So, imagine a server that is just running somewhere, and then whenever the query comes in, you just need to estimate the, you just need to compute the matrix C and then multiply B transpose A to that matrix C. And then you have the distance right there, okay? Now, just for the validation purpose, let's try to define the exact, okay? And the exact is going to be defined as a matrix of a size, size what? N number of references by number of queries. Is that right? Yeah. So basically, it's a matrix representing the distance from references, which are 4,000, to the queries, which is 150. And there you go. For the row index I, we're going to traverse over the number of references. For the column index J, we're going from 0 to NQ. And then the exact IJ, so we're repeating the same code, right? So that's basically why I put you guys into the breakout room so that you guys can have a chance to think about it. I'm just going to implement everything directly. So here, what you need to do is simply compute the distance from, X ref, ith row, and X query, jth row, and then take the square of the differences, take the summation, and then take the square root. Then that's the exact computation. And just out of curiosity, let's measure the time required to compute the exact distance matrix. And as you can imagine, it takes quite a bit of time. See, 7.4 seconds for computing this exact matrix, as opposed to 60 milliseconds for approximation. So it is quite obvious that, you know, in terms of computational time, there is a huge advantage. Now, is there an advantage in terms of the accuracy? Is it accurate enough? And for that, what I'm going to do is simply to find the difference between the approximated distance matrix and the exact distance matrix. And then I'm going to define, well, let's talk about the percentage. I think that's easier. So, with respect to the actual distance value, what is the percentage difference, right, between the approximated value and the exact values? So that's going to be percent error. And then our MSE of the percent error is going to be basically percent error squared, and then mean of the squared error is the mean square error. And then if I put square root to that, it becomes root mean square error. And that's the number that I'm interested in, and maybe multiply by 100 to make it a percentage. Oops. Oh, our MSE. What did I do? Oops. Why is it? Sorry, there's got to be a mistake. It can't be 164% error. Well, we have only 2 minutes remaining for this class, so instead of trying to debug, I think I actually have to wrap this up. But from my experience, with this much of a pivot, the error is roughly 20% in terms of percentage root mean square error. And then as you increase the number of pivots, kind of a sweet spot for this particular problem is about 100 to 200 pivots. And then if you use that much of pivots, the accuracy, the root mean square error goes down to around 5% to 10% error. So that's basically the number that I expect. But for some reason, maybe I made a mistake somewhere in my code. Right now it's showing 164% error. So, but I believe this is because some mistake that I made somewhere in my code. So I'm going to actually, after this class, I'm going to try to debug this and then find out a mistake that I made, and then I'll post it on Icon so that you have the full version that is working. But hopefully, at least you guys was able to understand the process of applying Nystrom approximation in terms of what is being computed in offline and what is being computed in online, and how we generate the result and so on and so forth. So as far as you are able to understand that, I think that should be sufficient for today's class. So again, I will upload a correct version of the code on Icon so that you have a full access to the working code. Other than that, thank you so much for joining today, and I'll see you guys on Thursday.